Programs are made of code and data. In a well-designed project, related code is grouped together and placed in functions. This is called modularization. Related data can also be modularized through the use of arrays and structures. Modularization is very important and a key concept in programming that allows effective and easy management of code and data. It can also aid with the readability and redundancy of your code. Arrays are modules which group data that are of the same type and have the same role in the program. All the grades a student has can be grouped into an array instead of using multiple variables. The members of an array are called elements, and they are accessed using a single variable name and an index number. An index is the location of a specific element within the array. Indices always start at 0 and increase. This means that the first element in an array is located at index 0, a concept which can be confusing to novice programmers. Let's reuse the averaging code from Module 1, grouped together as a single function. We're going to request numbers from the user, put them in an array, then call the function and calculate an average. For readability, it's usually nice to have the main function to be the first function you see. But if you remember the second golden rule of programming, define variables and functions before using them, we can't just do that. Fortunately, there's a way around that. By writing the first line of the function above main, followed by a semicolon, we can tell the compiler, hey, I'm going to be using this function later on, is that cool? And the compiler won't give us any errors. The advantage to doing things this way is that all of the functions that your program will use will be next to each other, close to your global variables, and all above main, so any other programmer can see at a glance what your functions are. Additionally, doing it this way means it no longer matters in what order you write your functions. This single line is called a function prototype. Naturally, there still needs to be an actual definition of the prototyped function with the body code later on in the source file. Creating an array is simple. As usual, declare its type and name. Now add square brackets. Within those brackets, we'll specify the number of elements we want in the array. We'll use 10. Remember that the index will start at 0, so the elements will go 0, 1, 2, 3, etc. up to 9, not including 10. So we've declared our variable in main. This means it's a local variable, not a global variable. Because one function can't access another function's variables, we need to pass the array to the averaging function. Start by going to the function declaration and inside the parentheses, add an int array. The name doesn't matter, but you should be aware that even if we call this parameter int data, it is not the same variable as the int data in main. This is a different one that has just been given the same value. Note that we include the square brackets to indicate it's an array of integers, not just a single integer. Now we have to remember to go up to the prototype and update it. The prototype needs to include any parameters the function needs. With that done, we now need to modify the body of the function to make use of the array. Since we aren't using n anymore, we can remove its declaration as well. We'll just comment it out. It's often a good idea to comment out unneeded lines first, just in case you make a mistake and need to put them back in. We can remove it properly once we know the changes work as intended. Replace n with data. Now that the function works with the array, we can call it from main, passing our data into it. Let's create a new function that displays all the elements in an array. Since it isn't going to return any data, its data type will be void and we'll name it view. It's going to have two parameters, an integer array d and an integer size. By specifying the size of the array, we'll be able to design this function so that no matter how many elements there are, we can still use it. Previously, we assumed the size to be 10. Create a for loop, declaring int I. The value passed into size will dictate the number of times we loop, so our condition will be I less than size, because we want it to loop for every element in the array. The increment will be I++. Beneath that, we just need a printf that outputs the element in the array with the index of I. For our next example, we'll modify the old code, or even code from Module 1, to use an array to store the user's inputs. We'll start by creating an array of size 100 to contain the data. In the loop, we need to start filling the array. Now we have an interesting pair of problems. Because each input needs to go in a new element, we need a counter variable that increments in every iteration. And because there's a size limit of 100 in the array, the user will only be able to enter 100 numbers or fewer. We have some interesting options for handling these issues, depending on what functionality we want the program to have. First, we could use a for loop in place of the while loop. This is good for a number of reasons. For loops come with a counter, usually called I, which is naturally suited to serving as the variable we use as the array's index. And as the condition, we can write I less than 100, which will cause the loop to end when the array is full. This solves both of our problems. The second way is to create a counter variable for the while loop and manually increment it. When it reaches 100, we can set it to 0, allowing us to go back to the beginning of the array and start overwriting the first inputs. When writing programs, it pays to keep in mind what your design decisions will allow the program to do. So in this case, let's take option 2 and modify the while loop. Let's define a new int before the loop to serve as the counter. Have scanf use the array data at index counter. We'll check to see if data counter is 0, and we'll also perform the odd-even test on data counter. Finally, modify the printfs to output using data counter. As a final addition, let's add a for loop after the while loop ends that will output the complete list. It'll start at 0 and go all the way up to the counter, which conveniently holds the total number of inputs the program received. If we had used a for loop earlier instead of a while loop, we would have to declare a separate variable to hold this information so we could use it now. Because of a concept called scope, which refers to the visibility and accessibility of variables, any variable declared inside a loop cannot be accessed from the outside. This is the exact same reason why one function's local variables cannot be seen by another function. Essentially, any counter used in a for loop is local to that for loop. So if we were to rely on I to hold the total number of user inputs, the compiler would have thrown an error claiming that I was never declared. Scope sounds confusing and annoying at first, but it does have significant benefits. For instance, you normally can't declare two variables with the same name, because then the program doesn't know which one you're talking about. But you can use int I many times in the same function when writing for loops. That's because when you're in the loop, the only I the program can see is the local counter. Outside the loop, it's invisible. Without scope, we'd have to use a different variable name for every for loop in our program, even if they're in completely unrelated functions. Anyway, all that's left to do is write printf and have it output data I. For the next example, we'll modify the code to store odd and even numbers in their distinct own arrays and list them at the end separately. Let's rename data to data odd. Next, we need to create a second array called data even. We need to change our counter to counter odd and add a second counter called counter even. We need a variable to hold the input before it gets added to an array, so let's declare int input and replace data counter with it. Make sure you are initializing your variables. Next, when the program prints whether the input is odd or even, we'll append the input to its respective array. For instance, odd data, odd counter equals input. Then increment the counter by 1. Rinse and repeat. Finally, duplicate the for loop at the end and adjust each of them to output one of the arrays. Before we move on, it's always a good idea to make sure the user knows what to do, so include a couple of printfs to give them instructions. If there is a group of related data that are not of the same type or have different roles within the program, we can use a structure to organize them. In C, structures act as a new, user-defined compound data type. This is an incredibly powerful feature. As a data type, structures can be used to define new variables. Because it's a compound data type, structures are made up of additional member variables. Let's say we want to write a program that collects student ID, 2 grades, and determines the grade point average. It's not a terribly complex program, but we do have 4 pieces of data. Here's the key question though. What if we want to add another student? Right now, that would require defining another set of 4 variables, bringing our total up to 8. What if we want 30 students? That's getting downright messy, as suddenly we have 4 pieces of data for each student all jumbled up together. And what if we want to pass the whole class of students into a function? You might as well give up at that point. But this is where structures really shine. Let's create a new struct above main in the global scope outside of any functions. It'll be called student, and we'll move our 4 pieces of data into it. Now in main, we'll create a new variable. Notice how the type is teal, not blue. That's because it's a user-defined type. Visual Studio differentiates between user-defined and standard data types to make it easier to read. To access the members within Gym, we write the name of the structure dot name of the member. So, gym.id gets us the value of int id within student gym. To modify the rest of the code to work with our structure, we'll write gym.id, gym.grade1, gym.grade2, and gym.gpa. That's it. But what if we did want a class of 30? Well, guess what? In the same way that we've been making arrays of integers, we can also make arrays of structures. Rewrite gym to say bit 2400 square brackets 30. We won't bother with a loop to go through all of them. We'll just access the first student in the class by replacing all instances of gym with bit 2400 0. This is easily done by hitting Ctrl F, clicking the down arrow on the left, writing gym on the top, and bit 2400 square brackets 0 below. After that, the program should run. Now we have 30 students, each with 2 grades, an ID, and a GPA. Structures are very useful for organizing and structuring your data. Be sure to make use of them if you think your variables are getting out of hand. The 6th golden rule of programming is modularization. Group related data into arrays and structures, and related code into functions. Modularization is very helpful when organizing and reusing code, reading and debugging code, reducing errors, and generally just writing programs faster. Don't ever copy and paste code without first thinking, can I write a function, loop, array, or structure to do this for me? Or make it easier? If you get into the habit of copy and pasting code, things start getting messy when you work on bigger projects with hundreds of lines of code. You never want to be in a situation where you don't understand what some code you wrote an hour ago does. Well, that's it for this part of Module 2 and an overview of arrays and structures.